All right, today we're going to begin our lesson talking about power. Power is our next step in talking about work and kinetic energy and all of that stuff. And so our goals today are to be able to calculate power maintained to the power required to keep an object moving, and calculate the work performed by a force that supplies constant power. It's pretty straightforward things. Now, power is an easy one. Power is just how fast work is done. I guess the fancy way to say that is the rate at which work is done. And that's pretty much it. So we'll get into the equation and look at what that means for us. So power being the rate at which work is done is going to be work divided by time. Now, real quick, looking at the units on that, work is measured in joules, time is measured in seconds. So a joule per a second is going to be a watt. W-A-T-T. We usually just use a W for that. So that's how we're going to, those are the units we're going to use for power. What can we do with it? Well, I didn't get it. All right. So power is work over time. If we remember what work is, that's, well, the first thing we had was force times change in displacement over time. But if we think back, change in displacement over time, well, that's just velocity. So we could also say that power is equal to force times velocity. And we use that to find the power developed by force moving an object, V, at a constant velocity. So if you're driving down the street against, let's say, 500 newtons of wind friction, your engine is supplying 500 newtons of force, and if you're driving at 10 meters per second, then your power is going to be that 500 newtons times the 10 meters second. That's the power that your engine is developing. We've got an example like that later on. The next way we can look at power, again, if power is work over time, the other thing that we know that work is the change in kinetic energy. So power can be the change in kinetic energy over time. The way we look at that, we're at it one more time. Power is kinetic energy final minus kinetic energy initial, with an F, over time. Or we have to write all of that stuff out. Power is 1/2 mv squared minus 1/2 mv initial squared, all over time. This would be if you speed up from rest to 60 meters per second in a certain amount of time. You can figure out how much power was required to do so. Okay, so regular work over time, force times velocity, and change in kinetic energy over time. All three of these are ways to calculate power. What we have coming up next are three examples that take us through some basic calculations. Alright, so for the first one, I have a man pushing a block with a mass of 15 kilograms across the floor, and he's using a force of 100 newtons. Now I want to determine the work the man does on the block if he pushes it 8 meters. Alright, well again, this is nothing new. Work is force times displacement. The man's force is 100 newtons. The displacement of the box is 8 meters. And so the work that we do is 800 joules. Now, the next thing that we see that we have to do is find the man's power output. Now, we just talked about power being work over time. But based on all the information given, I don't have time. Well, let's say we start off at rest. And our delta x is going to be 8 meters. And I'm looking for the time. Before I can do that, though, I need the acceleration. Thankfully, we have the man's force and the mass of the box. So that's just 100 newtons divided by 15 kilograms. And so our acceleration is going to be 6.66 meters per second squared. That gives us the acceleration, how far we went, and our initial velocity. We should be able to find the time. So if we use our third kinematic equation, delta x equals v0t plus 1/2 at squared, and plug in our knowns, that goes away because it's 0. We've got 2 delta x over a square rooted is equal to the time. So let's just plug everything in. 2 times 8 meters divided by 6.67 meters per second squared gives me a time of 1.54 seconds. Whew, that was a lot. Now that we have the time, we can come back up here and find the power. Power is work over time, so we're going to take the work that the man did, 800 joules, and divide it by how long it took him to do that, 1.54 seconds. So our power comes out to be 519.5 joules per second, which is going to be watts. It's a very basic power problem. Now, the next one. We're going to have a 500 kilogram car speed up from 30 meters per second to 60 meters per second in 7 seconds. And I'll have power output. Now, power is work over time. So that's force times distance over time. But I don't have any information about force or distance, so I can't use that equation for power. I do, however, have the mass of the car and 2 speeds for the car. I could probably calculate the kinetic energy. So that's going to be my change in kinetic energy over time, or 1/2 mv squared minus 1/2 mv initial squared all over the time. So I'm going to plug in some numbers. So the power is 1/2 times 500 kilograms times 60 meters per second squared minus 1/2 times 500 kilograms times 30 meters per second, and that whole quantity is squared divided by 7 seconds. When you plug all that into your calculator, you end up with a large number. 96,429 watts. And again, kinetic energy is in joules, that's in seconds. It's the correct unit. Now, part of our problem with watts is that they don't mean a lot to us as far as things go. But horsepower, we hear on commercials at least 8 times a day if you watch a lot of TV. So if I want to get this power in horsepower and not watts, I'm going to have to do a little conversion. So 96,429 watts, and my conversion factor is 746 watts per 1 horsepower. So this car had to have a power of 129 horsepower. That is roughly 1 Toyota Tercel. It's not a lot for a car. So that's another example of how to find power. Last one, and then we're done. What power is required to push a 10-kilogram box at a constant velocity of 13 meters per second against a frictional force of 50 newtons? All right, if I have my box, it's 10 kilograms. We got 100 newtons down, is the force of gravity. We have a normal force of 100 newtons up. And if we're going this way at a constant 13 meters per second, we know that there's a frictional force of 50 newtons. We'll say that that's equal to friction. So that leaves me with a problem. I don't know how hard I'm pushing. But I do know that this 13 meters per second is constant, which means my net force has to be 0, which means my applied force applied, is going to have to be equal to friction, 50 newtons. So I'm pushing with a force of 50 newtons. And I want to know the power required to push at 50 newtons at a speed of 13 meters per second. So power is work over time. So that's force times distance over time. I don't have a distance, nor do I have time, but I do know distance over time is velocity. So we've got force times velocity. So 50 newtons times 13 meters per second. So my power comes out to be 650 newtons times meters over seconds, which is 650 joules per second, or we could have just said 650 watts. And that's really it with power.